And welcome back. So let's consider object ownership. So move constructors and move assignment operators will allow you to define the semantics of a move operation for your user defined type. Now this might seem a little bit confusing, this idea of moving resources from one object of a particular type to an object of the same type. So let's go ahead and think about this as an explicit transfer of ownership of some sort of resource, of the resources owned by one object to another. Before we begin kind of considering cases where moves could be triggered implicitly. So let's consider object ownership. We say that the doubly linked list A, list B, as shown below, own a sequence of nodes accessible through their head and tail pointers. So in both cases, we have an entry point into our kind of sequence of nodes. We can either get into our linked list at the head, and if we wanted to perform a traversal, follow the next pointers until we hit the null pointer. Alternatively, we could traverse this linked list very easily in reverse. Just begin at the tail and follow the previous pointers until we hit the null pointer. Now the question becomes, okay, well, what if we wanted to transfer the contents of list A to list B? And in this transfer, let's assume that list A will be an empty list after the operation has finished. That is, list B will now own the resource that list A previously owned, and that no memory leaks will occur. So we have to consider two cases, or I guess one initial case here first, which is self-assignment or self-transfer per se. The reason being is that we're dealing with two doubly linked lists that have been built up. So one, consider self move. Two would be to clear list B. Three will be to update list B's pointers to list A's sequence of data. So in this case, head is going to point to there now. Let me get a brighter color. Head will point to the first node. And remember, we've deallocated these, so they don't exist anymore. Different color. Sorry about that. So head will now point to there. Tail will now point to the last node in the sequence that was once owned by list A, and it kind of still is, but we're going to go ahead and ensure that's no longer the case. Sorry, I keep hitting the erase button here. Is we're going to go ahead and set list A's pointers to the null pointer. So that's now going to point to null. Tail's now going to point to the null pointer too. And at this point, we have this. List B has absorbed list A's sequence of nodes simply by assigning the address of head and tail's pointers of list B to that of list A's. And then now list A is the empty list because the last thing we did was kind of complete. So at step 3 here, they shared a resource. After step 4, list A no longer pointed to the resource that it once owned, and now it kind of points to nothing. It's an empty list. So hopefully you can see how we got here. And again, the question was, how can we transfer list A's sequence of nodes to list B's? Very easy. It kind of begins with a shallow copy, right? We're just moving the addresses over in a member-wise copy. Then the last thing we're doing, though, is we're disrupting, terminating that shared resource in list A by updating its pointers to the null pointer. And at that point, nothing is shared between list A and list B. And we have this wonderful scenario here. So hopefully kind of the object ownership discussion helped a little bit here. This is where we're going with this, is this transfer of resource from one object of, say, some type to another object of the same type. So now we'll talk about how we can kind of implicitly invoke this move operation using the standard library's move function. And then we'll actually begin to define some move semantics for the doubly linked list that, again, you worked on in your doubly linked list MP, as well as the DNA splicing MP. And then after that, we'll conclude with a summary and some additional considerations.